Okay, so now let's do another example. For approximating these derivatives and see how we can do that. So example, second example, approximate d square u dx square, the second derivative of u with respect to x, at xi using the same 3 points. Okay. So let's see how we can do this. So we want to approximate this now the second derivative of u with respect to x, and this is x and this is u. At xi. Okay, so in this example, the previous example, we did it for the first derivative, and now we want to do it for the second derivative. So let's see what is d square u over dx square. So d square u over dx square, I can write it as d over dx of du over dx, right, at xi, and treat du over dx as u here, right? I can treat it as that, as a function, and so I can write it as this approximately equals to du over dx at, I'm going to write it at xi plus 1/2, and I have reason for that, and you will see how this will help us to get the derivatives at xi using those 3 points. So minus du over dx at xi minus 1/2 over xi plus 1/2 minus xi minus 1/2. Okay. So this is the first approximation, and let's see how we can do this now. So yeah, let me do this again because I change that. So I'm gonna draw this again and say, so let's see how we can do this. Okay, so I'm gonna draw it here. U, and this is gonna be x. Okay, let me just do it again. This is gonna be x. So let's plot the kind of example function. Okay, so this is x, this is u, and I'm gonna say This is xi. And this is ui. Okay. And the other thing is I'm gonna show here as xi plus 1/2 and roughly here as xi minus 1/2. Okay, so in order to find the second derivative at xi, what I'm doing is I am using the first derivative at xi plus 1/2 and xi minus 1/2. Okay, so let's see what are how we can write those down again. So I can write this down as this is also approximately equal to, I'm gonna write the first derivative here. So let me maybe yeah, let me write it with blue. So it's gonna be, yeah, let me change the colors a little bit so you can understand what I'm doing. So I'm gonna show this with let's say green. Xi minus 1/2. So the first derivative xi plus 1/2, I'm going to show it with as ui plus 1 ui plus 1 minus ui over xi plus 1 minus xi. So let's see what it is. So it means if this is your xi and your xi minus 1, right? So I'm going to show this as this. So the first one is going to be like that. This is the first derivative. And the second one, I'm going to show it as this line between these two. Okay. So the second one is going to be minus I'm going to use xui minus ui minus 1 over xi minus xi minus 1, right? Okay. So this is for the second derivative at xi, the first derivative at xi, okay? So then I'm gonna divide this by xi plus 1/2 minus xi minus 1/2, right? Okay, so this is how we can do an approximation for the second derivative. And now I want to further simplify this. So I can say if xi plus 1 minus xi equals to xi minus 1 And this equals to xi plus 1/2 minus xi minus 1/2. And all of these equal to delta x. Then I can write this relationship, which is the second derivative of u with respect to x at xi can be approximated as ui plus 1 minus ui over delta x minus ui minus ui minus 1 over delta x, all of them become delta x over delta x. And this equals to ui plus 1 minus 2ui plus ui minus 1 over delta x square. Right? So this is how you can actually approximate the second derivative of u with respect to x, right? So let me draw this. Okay, so we have approximated the second derivative of u with respect to x at the same points that we had before, I plus 1, I, and I minus 1, right? And it's very interesting that we got this result, and we can do this for, we have done this for du over dx and d square u over dx square, okay? So we are going to characterize the errors of this later when we, approximation errors of these later when we talk about truncation errors and Taylor series, okay? So before doing that, I want to give you some nomenclature and notations, operator notations, and then after that we can go to Taylor series in the next lecture. Okay, so some operator notations that you might have noticed here. So for forward difference, we have a forward difference operator when we are doing a forward difference in the in this approximation, and we show that with this delta. Okay, so delta ui is gonna be what? It's gonna be ui plus 1 minus ui. So this is a forward difference. The second one is a backward difference operator, and we show that with grad, and grad of ui equals to what? Ui minus ui minus 1. Okay, so this is a backward difference. And then we have a central difference. So central difference operator, which we show it with small delta. So delta ui, and these are all definitions. Okay, So delta ui is defined as ui plus 1/2 minus ui minus 1/2. Then we have the average operator, which we show it with mu, and mu ui is defined as 1/2 ui plus 1/2 plus ui minus 1/2. And finally, we have identity operator, which we show it as I, and as its name shows and indicates, it just returns the UI, okay? It doesn't do anything. It's an identity operator. So these are some famous operators and notations that we use in this finite difference scheme. And the thing I want to do is rewrite previous approximations in terms of the operator notation. So, for example, du over dx at I, for example, the first one, ui minus 1 over xi minus xi minus 1, right? So I can write this as so let me write first the ui. First write the approximation that we had. So it's ui minus 1 over xi minus xi minus 1, right? So as you see, both of them are backward difference operators, right? Both of them are backward difference operator. So I have to do this way. Delta ui, grad ui over grad xi, right? Because both of them are backward. So let's do the second one, backward difference. So the second one was du over dx at I. This can be approximated as or approximated equal to. So the second one, if you remember, was ui plus 1 minus ui over xi plus 1 minus xi. And this is a forward operator, a forward difference. So I'm going to show it with this, right? Delta. So it's going to be delta ui over delta xi. So the third one was du over dxi is approximated as ui plus 1 minus ui minus 1 over xi plus 1 minus xi minus 1. Okay, so this one is a little bit trickier, but This also can be written in this notation as delta mu ui over delta mu xi. Okay, so delta is a central difference operator. You apply that to the average operator, and then you are going to get these sums, these differences. Okay, so as a practice problem, show this equality. So do this at home, show this that this equality holds based on these definitions that we had. Okay. And the other thing that we can say is when spacing is constant, so when the spacing is constant, all of these operators, backward, forward, and central, all of them are going to have the same distance, right? So delta xi is going to be equal to grad xi and the centered difference operator, and they all equal to a constant delta x, right? So this is valid only if the spacing is constant. But if your spacing is not constant when you are doing finite difference, then this doesn't hold. For example, here, if the spacing is going to be different, then this statement is not going to hold. For example, if you have something here, if ui is here, xi is here, and then your xi plus 1 is here, and then your xi minus 1 is here, then this does not hold. So this holds only if all of them have the same distance. Okay, so this was just one note here, and in the next lecture we are gonna talk about Taylor series and truncation errors of these approximations, and we are going to find what is the order of accuracy of these approximations that we made. Okay, so let's just have a brief review. Finite difference method is a general numerical approximation method for solving PDEs, and the approach is we replace the derivatives by discrete differences. We replace the differential equation by a set of algebraic equations, and then we solve for a finite number of unknowns in the problem. So this is the general approach that we will see more clearly in the next lectures. And these approximations generally lead to second type of errors in numerical solution of PDEs, which are known as truncation errors, as we will discuss them soon. And then we solve two examples of these finite difference and in general approximation. If you are to approximate these function, a derivative, using these values of some discrete values at some points, what you are going to do. So we did this for a kind of imaginary function, something kind of we supposed a general arbitrary function, and then we found that we have these options. We have three options based on the way we are going to choose. So it can be like a forward, backward, or central kind of difference. And the questions were which one we have to choose, which one is better or worse, and are there any other choices? And these are the questions that we are going to answer in the next lectures. And then we did another example, which was approximating the second derivative of u with respect to x. And we did a trick by at the same points, 3 points, and then we did a trick to project those at the points to the first derivatives at the points where we can kind of use those same 3 points again. And so after that, we got to this approximation for this problem, which we will know later is a central difference approximation. And then we did some we just defined some operator notations for simplicity in these finite difference schemes as forward difference, backward difference operator, central difference, average operator, and identity operator. We rewrote those previous approximations in terms of these new operator notations, and then we just made a general statement about spacing. If it is constant, all of these forward, backward, central, all of them are going to be equal to each other. Okay, thank you very much.